Good day, everyone listening to me. This is a paper titled Weibull-Extended Pranav Distribution Application to Lifetime Datasets. It's a paper that we are presenting today, Monday, August 17, 2020, at the Bernoulli IMS One World Symposium 2020. The authors there on the paper are Badmus NI from Department of Mathematics, University of Lagos, Akoka, Nigeria. Amsa SO and Ajiboye Wayo, they are from Department of Statistics, Yaba College of Technology, here in Nigeria. Then this is the outline of our paper presenting today. Introduction to the appendix. Then the introduction, when we are talking about mixed or convoluted distribution, it's not a new thing. It's just a thing that has been in an existence for decades, and several authors, researchers, scholars, they have written one thing or the other, and we have so many methods that we can use the link to develop models or distribution like that. So we just mention a few of them. Exponential method introduced by Mood-Opler and Scrivasta 1993. Generator approach initiated by Eugene Ito 2002. Then beta link function introduced by Jones 2004. Then Weibull link function by Tahir Ito 2016. Now the objective. So we have our objective. Number one, to develop a new continuous distribution called Weibull-Extended Pranav distribution using Weibull link function as our method to develop it. Then to derive and obtain some statistical properties of the proposed distribution, like moments, generating function, other statistics, reliability, hazard function, and so on and so forth. Then to show the flexibility of the proposed distribution over other competing distribution using two different real-life data sets. Then the materials and method. So we use Weibull link function, the density and the distribution function by Tahir Ito 2016 and used by Leren Ito 2018 are being defined in 1 and 2. That is equation 1 and 2. Then where we have the lambda and the theta, small GY and capital GY are shape parameters, PDF and CDF of any continuous distribution that we can substitute there. So after substituting, we have what we have in 3 and 4, but the A and B there are the baseline distribution PDF and CDF introduced by Uwaime Ito 2018. So where we have the A and B, so when we slot it there, so it gives us the 5 and 6, which is the PDF and CDF of the proposed distribution. So the lambda and theta are just the two additional shape parameters to the existing shape and the scale parameters that we have, so that we have 4 parameters Weibull distribution that we are introducing now. So the PDF and the CDF of the proposed distribution is being showed in figure 1. So where we have, so if you look at it very well, you will see that the distribution, the proposed distribution, can can go with any kind of scale data because of its flexibility. Now here we present some of the statistical properties like survivor function, hazard function, reverse hazard function. Then the plot of survivor and the hazard function are being showed here. Then some statistical properties also are obtained here, so like moments and moment generating function, which we have in 11, then the generating function which we have in 13. So where we have our A, B, C, D and E, so we have it in appendix A, the slide that contain the appendix A. So we have it there. Then the other statistics also. So we have the minimum, we have the maximum other statistics there. Then here also we estimate using the maximum likelihood estimate, so to obtain the distribution parameter lambda, theta, beta, and alpha, which we have as shape and scale parameter. So then we have the likelihood function of it, which leads us to all the partial derivatives which we have in appendix B. Then the application to real life data sets. So we have two real life data sets, and we compare it with 7 of the existing distribution, so which we have as extended Pranav distribution by UYME 2018, then to a district Pranav distribution by Abebe and Shukla 2019. Then we use some model selection criteria there, so like AIC, BIC, CIC, and HIC. Then the data are being that we use are 2 sets of data. So we have one from Fuller Ito, which is strength of data of glass of the aircraft window, so reported in Fuller Ito 1994, then used by UYME 2018. Then you can see from the skewness of the data that the data is not, it's a skewed data, it's not a normal data. Then likewise in the second one, which represent the tensile strength measure in GPA of 69 carbon fibers tested under tension at gauge length of 20 mm, so by Beda and Priest 1982, and used by Shukla 2019. Then also we can see the PDF, the estimated PDF for the data, so used for the distribution. Then we have our proposed distribution and the existing distribution which we use against it. Then we have the result here, which you can see clean and clear here, that the result from the proposed distribution is smaller. All the values under the proposed distribution are smaller than any one of them. It means that the smaller the value of a model or distribution is, the better representation it is to the data or to such data. Then we can see in both data that we use is being used and used well. Then discussion, under discussion and conclusion, a new distribution called Weibull-Extended Pranav distribution has been introduced using Weibull link model, as we have been saying. Then which has its baseline distributions from extended Pranav and Pranav distribution by UYME 2018 and Shukla 2018. Then we derive and obtain some statistical properties of it, and we apply it to 2 examples of real life data sets, so which the extended Pranav Weibull-Extended Pranav distribution represented them well, more than other. Conclusively, result from the analysis in table 3 now indicate that the Weibull-Extended Pranav has the lowest value, so on the selected criteria that we have. Meanwhile, it shows and proves its superiority and flexibility over others. The reference, these are the references that we have there. Then the appendix are in the next slide. Thank you all for listening.